Hello, my name is Rebecca Muller. During today's lesson, we're going to consider how linear functions can be used in application problems. Let's look at our first example now. The following formula gives the surface area of a cylinder in terms of its radius and height. Solve this formula for the variable h. Notice that what we're given is sometimes called a literal equation. It's a formula for surface area. The variable h is here in this term, but notice we have other terms that involve other variables also. We're going to begin by trying to isolate the term by subtracting 2 pi r squared, that is, from both sides of the equation. We end up with s minus 2 pi r squared equals 2 pi r times h. I emphasize the fact that what's going on between the h and the other values, that is, in the term, is multiplication, because we know that in order to undo multiplication, we end up using division. Therefore, we're going to divide both sides of the equation by 2 pi r in order to get our final value for h. We can then write s minus 2 pi r squared divided by 2 pi r equals h. And we've solved this linear equation for h. The next examples we're going to consider are what are normally called word problems. And in order to solve these word problems, we're going to use a four-step process called Polya's four-step problem-solving process. And this is basically a logical means of going through a problem. First, we want to understand what the problem is asking us to do. Next, we want to devise a plan in order to solve the problem. Third, we carry out the plan. And finally, we need to remember that once we've gotten a solution, we want to look back and make sure that that solution makes sense in our problem. As our first problem situation, we want to look at the dimensions of an aquarium, given as follows. The front of a rectangular aquarium has a ratio of its length to its width of 5 to 3. The perimeter of the rectangle is 64 inches. Find the length and width of the rectangle. In order to solve this problem, what we want to consider are what we should have allowed the variables to equal. Let's begin by identifying our unknowns. We know that we're trying to find the width and the length of this rectangle. We're told that the ratio of the length to the width is 5 to 3. If we let the value for the width equal x, then our length ends up being 5/3 x. That's how we write down the ratio as 5 to 3. Next, we're told that the perimeter is equal to 64 inches. Recalling a formula from geometry, we have that the perimeter of a rectangle is 2L plus 2W. We can substitute then for P as 64, and L, we're using the setup that we have at the top of the screen, 5/3 x. And for W, we chose the variable x. Now, simplifying, 64 equals 10/3 x plus 2x. 64 is going to equal 10/3 plus 2 is the same as 6/3. So what we have is 16/3 x. And next, we're going to multiply both sides of the equation by 3/16. What that will end up doing is to multiply by the reciprocal value in order to end up getting a coefficient of 1 for x, and we come up with 16 goes into 64 4 times, 12 equals x. Let's remember that x is the width, the length was 5/3 times x, so this is going to be 5/3 times 12, and 5/3 times 12 3 goes into 12 4 times, we come up with a length of 20. So using the values, the units that we were given in the problem, we have a perimeter of 64 when we have a width of 12 and a length of 20. Our second example is going to work with a problem called a mixture problem. And here we're going to be considering what happens when we're trying to mix pure acid to some percentages in order to come up with a higher percentage or strengthening of our solution. Here's the problem. Acid mixture. How much pure acid should be added to 6 liters of 30% acid to increase the concentration to 50% acid? In this problem, we're trying to find out how much pure acid we have. In order to figure that out, we're going to have to use the percentages that we're given. Let's begin by identifying what we're trying to find. Here we want to let x equal the amount of pure acid. We're told that we have 6 liters of 30% solution. In order to use that in our equation, what we can write down is that that 30% of 6 liters will be added to the pure acid. Now, we know that we have X amount of it, but the percentage that we're going to have to use is 100% because pure acid is 100% acid. So we can write that down in decimal form as 1 times X. And finally, we want to end up with 50% acid solution. So we have 50%, but we also have to know what amount we're dealing with. Here we have 6 liters, here we have X liters, so adding those together we get 6 plus X as our amount. In order to simplify matters, I'm going to multiply both sides of this equation by 100. That will give us 30 times 6 plus 100X equals 50 times 6 plus X. Now we can multiply out in order to simplify the equation and solve for X. Multiplying 30 times 6 gives 180 plus 100X equals, distributive property here gives us 300 plus 50X. We can subtract 50X from both sides of the equation and get 100X minus 50X is 50X. And we'll also at the same time subtract 180 from both sides of the equation. 300 minus 180 is going to give us 120. So we have 5X equals 120. Dividing both sides of the equation then by 50 gives us a value of 2.4. Now, we're going to verify these results by looking at the graphs on the graphing calculator. We'll input the left-hand side of the equation into y sub 1 and the right-hand side of the equation into y sub 2. Y sub 1 will end up equaling 0.3 times 6 plus X. Y sub 2 will end up equaling 0.5 times 6 plus X. I'll go to a standard viewing window. There's the left-hand side of the equation. There's the right-hand side of the equation. We'll be looking for the point of intersection. Second, calculate the intersection point. Y1 is our first equation, Y2 is our second equation, and we can move over to what looks like the intersection point and press enter. And notice that we end up with the value of 2.4 as we had found it in the problem. What this means is that in order to end up with a mixture as we wanted, we have to add 2.4 liters of pure acid. Now, we will also have an application in linear equations called direct variation, and that's what we're going to consider next. Direct variation gives us the following situation. A number y varies directly with x if there exists a non-zero number k such that y equals k times x. K is called the constant of variation. Let's see how this plays out by looking at the following example. The pressure of a liquid problem. The pressure exerted by a certain liquid at a given point varies directly with the depth of the point beneath the surface of the liquid. If the pressure at 30 feet is 15 pounds per square foot, what is the pressure exerted at 70 feet? Now, this problem can seem like it's a little overwhelming at first until you realize that the equation that we're going to use is just simply the form y equals a number times x. K times x is what we'll begin with. Here we're told that the pressure exerted by a certain liquid varies directly with the depth of the point. So what we have is that pressure varies directly with depth. We can write that down if we allow pressure, the amount of pressure, to equal our y variable, and the depth we'll give by using our x variable. We have the pressure varies directly as the depth. So we write down y equals k times x. Now we're going to try to find the value of k in this formula. And the way to do that is to use the values that we were given in the original problem. We were told that at the depth of 30 feet, so we could put in 30 for x, the pressure was 15 pounds per square inch. Per square foot, that is. So we have 15 equals k times 30. Now to solve for k requires us just to divide both sides of the equation by 30, and what we get is 15 over 30, which is equal to 0.5. Now, what that means is that we can write down y equals 0.5x as the formula which gives us what happens to our pressure according to the depth that we're dealing with. We can look in at our graphing calculator in order to find certain values of what we end up getting in the problem. For instance, it asks us what is the pressure exerted at 70 feet. Let's go back and clear out our screen, and we're going to insert into our equation y1 the equation we came up with, 0.5x. Now I'm going to go to table set, and I'm going to again use the ask feature, and when I go to my table, it asks me what is the value that I want to input. I'm going to put in 70, and it tells me that the value is 35, which of course makes sense because we know that if all we're doing is multiplying by 1/2, then what we end up with is 35 here. So at a depth of 70 feet, we have 35 pounds per square foot of pressure. As our next example, we're going to consider an application from business. Let's look at a delivery service and what happens in a case of someone trying to go in business for themselves. Lane Vosberg operates a delivery service in a southern city. His startup cost amounted to $2,300. He estimates that it will cost him, in terms of gasoline, wear and tear on his car, etc., $3 per delivery. He charges $5.50 per delivery. Let X represent the number of deliveries he makes, and find the cost and revenue functions in terms of X. Also, we want to find the value of X for which the revenue equals the cost, or where C of X equals R of X. So let's begin by setting up the function for cost. C of X equals. We're told in the situation that his original cost were $2,300. So we can write that down as part of our cost. But we also have what are called variable costs. These are the fixed costs. Our variable costs are $3 per delivery. So we can write down $3 for each delivery that he makes. Next, we're told that the revenue, the amount of money that he brings in, is equal to $5.50 per delivery. So we can write down R of X equals 5.50x. So we've come up with the two formulas for the cost and the revenue. We next would like to find the value of X for which the cost equals the revenue. To do that, we simply set the two functions equal to each other. 2,300 plus 3x equals 5.50 times x. Subtracting 3x from both sides of the equation gives us 2,300 equals 2.50x. And finally, dividing both sides of the equation by 2.5, we get that x equals 920. Now, what that relates to in the problem is that he needs 920 deliveries in order to break even, where his cost and his revenue are the same value. We call this, obviously, the break-even point. On the graphing calculator, we can also do the same problem. We're going to put the cost function into y1 and the revenue function into y sub 2. And then we'll have to change our window in order to depict what's going on in the problem. So clearing out y sub 1, we end up inputting the cost function, 2,300 plus 3x. And our revenue function is 5.5x. You could put 5.50 if you'd like. Now, we have to consider what's going on in the problem in order to set a good window here. What we know is that X stands for the number of deliveries that he makes. So the least number of deliveries could be 0. Let's pick a high number of deliveries in order to give us a starting point. We'll choose 1,500. And I'm going to make my scale 100. Our Y value stands for the amount of revenue. Obviously, the smallest amount of revenue you can make is nothing. The largest amount, again, I'm going to choose a fairly large value. $10,000 would be nice to make in a week. We are going to then end up having our Y scale equal to 1,000. Graphing these two functions, what we'll be looking for the break-even point would be the intersection of the graphs. We can see that our break-even point is here. To find it in the calculator, we're going to do, again, our intersection method. Our first curve is y1, second curve is y2, and putting our guess approximately on top of that point, we find the intersection verifies what we had found analytically. We end up with an intersection point of 920. By the way, the value of 5,060 that was given there would be what his cost and his revenue were when they were equal. We'd now like you to try one of these problems on your own. So let's look at an example that's similar to the example we just finished with, having to do with cost and revenue. Rebecca Isaac Fahey stuffs envelopes for extra income during her spare time. Her initial cost to obtain the necessary information for the job was $200. Each envelope costs 2 cents, and she gets paid 4 cents per envelope stuffed. Let's let X represent the number of envelopes stuffed. The first thing that you want to do is express the cost C as a function of X. Next, express the revenue R as a function of X. And finally, determine the break-even point. Turn the tape off now and try this problem on your own. Then turn the tape back on in order to check your work. Now let's see if you were able to solve the problem. We're told that we are going to let X equal the number of envelopes that she ends up working with. We want to come up with a function that gives us the cost of her business. We're told that her initial startup costs are $200, so we can write down 200. And we're also told that it costs her 2 cents per envelope, so we can write down 0.02x. Make sure you're using decimals here because you've already used 200 as dollars, so this has to be in the same unit. Next, we want to write down what her revenue is. Her revenue, we're told, is 4 cents per envelope that's stuffed. So we can write down 4 cents per envelope. Did you get the cost and revenue functions right? Well, now let's see if you can get the break-even point. All we have to do is set those two functions equal to each other. We have 200 plus 0.02x equals 0.04x. We now subtract 0.02x from both sides of the equation, giving us 200 equals 0.04 minus 0.02 is 0.02, and then that's the coefficient on x. Next, we divide both sides of the equation by 0.02, and we end up with 10,000, which is a pretty nice number of envelopes that she's going to have to stuff. It turns out that if she stuffs more than 10,000 envelopes, she'll end up making a profit. But if she doesn't stuff that many, she'll end up being in the red. You've now looked at a number of applications for linear functions and equations. It's time to try a few on your own. Use the exercises at the end of the section to try some.